Questions about anything? Yeah.
For this inequality to hold, should the functions just be 1 and sine x cosine of x? Because if we take them as the normalized functions, like these are orthonormal.
The normalized functions would give you something, and when you collect some of those coefficients and stick them on the other side, the pi business, that's where the 1 over pi comes from. So, yeah, those are the Fourier coefficients. Those a's and bn's are the Fourier coefficients, not the coefficients that come in Bessel's inequality, but they're related by constants involving pi. And when you collect it all together and look at it, that's what you get. It's not so critical for us at the moment what that is right there, but the fact is that inequality means that those coefficients have to tend to. That means that sum of positive terms, or I should say non-negative terms, converges, and that means that tail end of the series there has to go to 0. And that means the corollary that's significant for us is that the Fourier coefficients of a piecewise I didn't mention that we're dealing with piecewise continuous functions last time, but those integrals all make sense if f is a piecewise continuous function, meaning it's continuous on intervals and might have jumps, finitely many jumps. So Fourier coefficients of a piecewise continuous function on minus pi tend to 0 as n goes to infinity. And that turns out to be true in the real or complex case. So they go to 0 as n goes to infinity. For both the real and the complex version. That's exciting news for us. And that corollary is going to allow me to show you that this big fact today, that I'm going to show you that Fourier series converge to the function they're supposed to converge to. So today, theorem, I'm not going to, it turns out not to be enough to assume that f is piecewise continuous. I need to assume more than that. And to begin with today, I'm going to assume that f is C1 smooth meaning f is continuous, its first derivative exists, and is also continuous. So we are going to assume f is C1 smooth on R and 2 pi periodic. So what does that mean for, we've all been looking at integrals from minus pi to pi. What it means is that it means that the minus pi end hooks up with the pi end. So not only the values agree, but the derivatives agree, so there's no kink. There's no kink there when I extend it as a periodic function. So it's nice and smooth. In fact, so it means if I started with minus pi to pi and stipulated the value at minus pi is the same at pi, and the derivatives are the same, then we could hook those together when we did the 2 pi periodic extension. That's what it means, basically. So I assume f is C1 smooth on R and 2 pi periodic. Then the Fourier series, let's see, the Fourier series, let's write what the Fourier series is. there's two ways to write the Fourier series, and they're the same. So let's see, the real version is A naught plus sum as n goes from 1 to capital N, an cosine nx plus bn sine nx. And I showed you recently that that's the same as the complex version as n goes from minus capital N to plus capital N, Cn e to the I nx. So either way you write it, that's the partial sum. I'm going to call that Sn of x for the nth partial sum of the Fourier series. Then that thing, Sn of x, converges to f of x at each point. In the interval minus pi to pi. In fact, it does it on all of R, because if you know it on that interval, then you know it on all R by 2 pi periodic extension. Okay. Well, it turns out this is not going to be terribly hard once we have that Bessel's inequality fact. I will need a little lemma about periodic functions. If f is 2 pi periodic, then it turns out that the integral along any interval of length 2 pi is the same. Okay, so if it's 2 pi periodic, then the integral from a to a plus 2 pi, whatever a is the same as the integral from minus pi to pi. So that's an easy lemma. Let's see, I'll give you a picture proof, which can be turned into a boring math proof if you want. Let's see. So what I'm going to draw a picture here of see if I can draw a reasonable function. Let's go from minus pi to pi. Here's my function on minus pi to pi. I should have worked on this at home. I'm going to make it go. Yeah. Okay, there's that. And now, notice that I made it hook up. They're going to hook up here. And I also was careful to make it have the same derivative there, so that when I extend it, let's see, I should cheat. I'll go like that. Control copy, Control V. Hook it up there. Let's do it again. Hook it up there. Okay, let's see. So I'm going to integrate from a to a plus 2 pi. So let's put our a so a would be the same distance over here to a plus 2 pi. Okay, that integral would be a certain area. And if you think about that area, I could go from a to pi, and all I have to do is pick up this piece pick up this piece and stick it on here. That area is the same. So you see, if I go from minus pi to pi, it's the same as if I start at a and go to a plus 2 pi, because all I have to do to get that is pick that up and move it over there. Right? Doing that when you start writing it out is kind of, you'll realize, oh, to explain that, so pick it up and move it. And you'll see this fact. Was there a question back there?
Yeah. When you said it converges at every point, does it also like converge uniformly?
That's a tougher question. I'm just going to show that it pointwise converges today. And you'll see that, I probably could do some sophisticated estimates, but I'm not doing that yet. I'm just getting the basic fact that it pointwise converges. And the question about uniform convergence is going to require more thought. Okay, so that's a picture proof of that lemma. Not hard. To say it in words is harder than drawing a picture, but once you see the picture, it wouldn't be hard to do the words. So let's see, the proof of the theorem now. It's going to be fun. I've been dying to do this. Let's see. Now, this is a case where the complex version of the partial sum is going to be useful to us. Okay, and remember that what those CNs, I'll make those CNs red. Those are the complex Fourier coefficients. And let's see, that would be a sum as n goes from minus n to plus n. And that Cn, remember, is 1 over 2 pi integral from minus pi to pi of f of t e to the minus int dt. And now I multiply that by e to the inx. Well, e to the inx is a constant in that integral. So I'm going to move it inside. And by the way, your homework convinces you that those calculations you do with complex integrals are valid. So I can move this constant inside the integral. In fact, I'm going to stick it right there. And so now I've got, let's see, and in fact, that's step 1. And then step 2 is to interchange the integral with the sum. It's a finite sum, so there's no problem doing that. And so what happens when I do that, 1 over 2 pi's carry along, and I get here a sum as n goes from minus n to n of, let's see, what's this thing? I'll have e to the I n x minus t, n times x times n times x minus n times t, so I can collect those together. I got that. And that would be times f of t, which I can pull out of the sum. And fortunately, I've prepared you for this moment. That is the famous Dirichlet kernel we messed around with the other day. So, this thing right here is the Dirichlet kernel. Let's see, so I'm going to write dn of t. And today, notice there's a 1 over 2 pi there. I left that out last time. I should maybe put it in there. I didn't want to write 1 over 2 pi over and over again that day. But this is new. I'm adding a 1 over 2 pi in my Dirichlet kernel. So the Dirichlet kernel is the sum as n goes from minus n to n of e to the int. And I used geometric series to sum that up and give you a nice formula for it when you add it in, when you use de Moivre's formula and play games. That's the Dirichlet kernel, and that's where it comes up in Fourier analysis. So here's a wonderful formula. The nth partial sum in a Fourier series is given by the integral from minus pi to pi of the Dirichlet kernel at x minus t. Notice inside that integral there, the theta is x minus t. So that's the Dirichlet kernel at x minus t times f of t dt. That's cool. Let's recall the facts about the Dirichlet kernel. We worked out most of these before. Important fact number one is the integral from minus pi to pi of the Dirichlet kernel, with me dividing by 2 pi this time. Instead of being 2 pi, it's a big fat 1. That's nice. And then number two was the fantastic formula. dn of t is, let's see, because I added the 2 pi this time, I should maybe mention the 2 pi is new here today. I didn't put it there the last time I wrote this down. And some books either don't put the 2 pi or they do. Stein does. So the Dirichlet kernel is 1 over 2 pi times the famous formula sine n plus a half t over sine t over 2. That's if t is unequal to 0. Of course, if you look at that sum, that's not bad at 0. Nothing bad happens. But that formula looks like 0 over 0. So in fact, L'Hopital's rule shows you that dn at 0 is, when you do L'Hopital's rule, 1 over 2 pi n plus a half over a half. Which is n plus a half over pi. That's if t equals 0. Okay. And there was that graph. I showed you the graph last time. I won't draw that graph again. Oh, and not something else I didn't mention last time because I didn't care about it. But it's 2n dnt is 2 pi periodic. That's because everything in the sum is 2 pi periodic. So let's see. Let me mention the proof of 1. Integral from minus pi to pi of the dn of t dt. When I write out the sum, there's only one term that matters, and that is the constant 1 term. So the n equals 0 term is 1 over 2 pi times 1 dt. That's the n equals 0 case. And the n unequal to 0 case, so plus a sum as, let's see, so n would be absolute n would be less than or equal to n and not 0. Those integrals would all be integrals of exponentials, which are cosine and sines, remember. When you write them out in real and imaginary parts, you'd get e to the int dt. And all of those are 0. If you were to calculate those with your bare hands, you maybe would write e to the int equals cosine nt plus sine nt. And those have as many humps above the x-axis as below. And so they integrate to 0. Or you could just calculate those and see that. And this one is the one that spits out 1 over 2 pi times length 2 pi is 1. So that equals 1 plus a sum of zeros equals 1. So that's easy. And then when you look at that sum there, you realize, so the proof of 3, all the terms are 2 pi periodic. All the terms in dn are 2 pi periodic. And number 2 I did a couple of lectures ago. Those are the good things about dn. Here's some bad things about dn that make Fourier series interesting. I'm not going to prove these today. So bad things are dn of t is not a positive function. On the interval where it's defined, or it's defined on R, but in particular it's not positive on our favorite interval. Stein is going to use a word good kernel, and good kernels are going to be positive. So this is the first inkling we have that the Dirichlet kernel is exciting but not good in the sense of Stein. In fact, another bad thing about it is when you integrate it from pi to pi, the absolute value. We know the integral of the function itself is 1, but if you integrate the absolute value, that goes to infinity as n goes to infinity. So instead of canceling, those humps add up. It's too subtle to think about making those humps cancel. So that's a bad thing. But we'll save those bad things to think about later. So let's continue the proof. Okay, so I've got that formula I was excited about. Sn of x is the integral from minus pi to pi of the Dirichlet kernel at x minus t times dt. dt. Oops. I'll say f of t dt. Now I want to change variables. I want to get the x minus t or something like it in the f function and get it out of the Dirichlet kernel. So to do that, I'm going to call this, I'm going to do a change of variables and call that tau. So tau is going to be equal to x minus t, which means t is equal to x minus tau. Okay, that's going to be good. That's going to go in the f function when I mess around with it. And of course, let's see if t is this, then d tau is equal to minus dt. And we got to think about what happens to the endpoints. The bottom endpoint is minus pi. when t is equal to minus pi, tau is equal to x plus pi. And when t is equal to plus pi, tau is equal to x minus pi. And so this integral here is going to become equal to, let's see, it's going to be, tau is going to go from x plus pi to x minus pi. That's a backwards kind of integral. And here I'm going to get dn of tau. And here I'm going to get f of x minus tau. And dt is minus d tau. And then when I flip that integral to go starting from x minus pi, I can use that minus tau there, that minus d tau, and get that that's plus the integral from x minus pi to x plus pi of dn of tau f of x minus tau d tau. And now I can change my t to a, I can change my tau to a t. Change the tau. It's just a dummy variable. So I'm going to change the dummy variable. So this is just freshman calculus. Tau back to t. And what I get, I'm going to use my lemma. My lemma said that the integral along any interval of length 2 pi is the same thing, and I might as well take the integral from my Sn of x is going to be the integral from minus pi to pi of dn of t times f of x minus t. So all I've used today is freshman calculus. And now I've got to subtract f of x from that. And here's the fascinating thing. I can make f of x look exactly like that integral, kind of. So here's a brilliant idea that I don't know how long it took my heroes from that period to do it, but they noticed that f of x, of course, is equal to 1 times f of x, and 1 is equal to the integral of the Dirichlet kernel. Okay, that's 1 times f of x. I'm making a big deal out of this. Maybe it's going overboard. That's equal to 1. And so I can write f of x as a very similar looking thing. Integral from minus pi to pi of dn of t. Instead of that thing there, I would just have an f of x dt. And notice how similar that looks to this red box. That's an important red box at the moment. And I'll put this in red box too, why not? Because I'm going to combine them now. And so the fantastic thing is finally I can write Sn of x minus f of x. I'll stick them under one integral. Integral from minus pi to pi. Dirichlet kernel just sits there. And I get here f of x minus t minus f of x. The work is over now. I'll show you in a second. I need to see that this goes to 0 as n goes to infinity. like red boxes. This is good stuff. So this is the next red box. You can forget about the previous two. Well, let's see. So we know what the Dirichlet kernel is. Let's write. This mass is equal to the integral from minus pi to pi, the Dirichlet kernel, 1 over 2 pi sine n plus a half t, with the understanding that that's not doing anything bad at t equals 0, times f of x minus t minus f of x dt. Okay, so now I'm going to use the fact that I want to get Fourier coefficients in there. And the n is inside of a sine n plus a half. That's bugging me. I want to get that n, I want to get that plus a half out of there. So I'm going to use the trig identity that sine n plus a half t, when you do the trig identity, is sine nt cosine t over 2 plus cosine nt sine t over 2. And so when I put that, let's call this mess here star. When I use that in there, I'm going to get that star is equal to, let's see, it's going to be equal to 1 over pi times the integral from minus pi to pi. This is exciting. Sine nt. That's going to look like a Fourier coefficient. And now here, I'll put that 1/2 up here. 1/2 cosine t over 2. That's a nice function. And now I'm going to have f of x minus t minus f of x. That's 0 when t is equal to 0. And I'm dividing by sine t over 2. Well, that's not a bad function because of L'Hopital's rule. There's nothing bad about that at all. I'll call this g of t and show you that this is a nice continuous function. And so, in fact, that's going to be the Fourier sine coefficient in the Fourier series for a nice function. And so that's going to go to 0 because as I let n go to infinity. And so let's call that one g of t, and I'm going to call this one h of t. I'll show you both those things are nice. And let's see, I'm not quite done with this. I'd have a similar thing, plus 1 over pi, integral from minus pi to pi, cosine nt, which is going to be the cosine term in a Fourier series. Now let's see, what do I get there? That would give me 1/2 sine t over 2 in the formula for the sum of angles. And then I get that same old g of t. F of x minus t minus f of x divided by sine t over 2. I'll call that a g of t. Let's see, I used a g of t, didn't I? I'll call this h twiddle of t. Slightly different than my h above. But this is the same old g. And so the aha is these are the nth Fourier coefficients for nice functions. It's actually the real Fourier coefficients, an and bn, for nice functions. In fact, for a continuous function. Nice continuous functions. On minus pi to pi. So the theorem we started out with, they go to 0. So they go to 0 as n goes to infinity. And that shows that Sn of x tends to f of x as x goes to infinity. What am I saying? As n goes to infinity. Done. Okay, so I need to show you those are nice functions. So why they're nice? Why they are nice. Let's see. G of t, remember, was f of x minus t minus f of x over sine x over 2, sine t over 2. Well, sine t over 2 doesn't do anything bad, but let's think about it. That's equal to 0 at t equals 0. And this is equal to 0 at t equals 0. And L'Hopital's rule, if I let t goes to 0, limit as t goes to 0 of g of t, it's going to be equal to, let's see, when I do the limit, I differentiate with respect to t on top, and that would give me what? Minus limit. That would be equal to the limit as t goes to 0. The derivative on top is f prime of x minus t. Minus that. Because I have to use a chain rule, and there's a minus t. So it's minus that. The derivative of sine t over 2 would be 1/2 cosine t over 2. And that limit would be minus 2 times f prime of 0. So that g is actually a continuous function if I give it the right value at 0. Also note, I'm not sine t over 2, the graph looks like this. Minus pi to pi. Sine t over 2 looks like that. So the only place where sine t over 2 is 0 is at the origin. The rest of the time you're dividing by something that's not 0. So nothing bad happens in the denominator except at t equals 0, where you use L'Hopital's rule to see that g is continuous there. So we see g of t is continuous on the interval minus pi to pi. And so you go back and, now that I know what g is, you go back and look at h. Well, h is just multiplying g by cosine t over 2, which is a wonderful function. And h twiddle, you multiply by sine. So interesting, that sine coefficient is the sine coefficient for that h of t, which is nice, and I know it goes to 0. And this is a cosine coefficient for a different h, but I know that goes to 0 too. So the Bessel's inequality gives me that both of those things go to 0. Okay. H of t was, what was it? I should look at it again. H is a cosine and H twiddle is a sine. H of t equals 1/2 cosine t over 2 times g of t. Nice. And H twiddle of t is 1/2 sine t over 2 g of t. That's nice. So I'm done. So the fascinating thing is that Bessel's was kind of an easy thing that just popped out of integrating orthogonal functions. But Bessel's is what we're used here. Bessel's inequality implies that Sn of x goes to f of x for each x. That's called pointwise convergence. We don't know anything about how fast or if the derivatives converge. But that's exciting. That means that if Johann could have showed his brother that, it would have made history different, maybe. They'd be called Bernoulli series instead of Fourier series. But the big question is, how fast? If you're going to do numerical things with computers and actually use this stuff, you really want to know. You want to know how many terms do I need to take in the series to get it within 1,000th of the function. That's an important thing. But the feeling is, the smoother the function, the faster the convergence. And we'll see why that feeling is valid. The smoother f is, the faster the convergence is. So next time I'm going to show you this. Next time. If I add 1 degree of differentiability, f, if f is C2 smooth and 2 pi periodic, so even better than today's f, then I get uniform convergence. Sn of x minus f of x is less than some constant, m, divided by n. For some constant. So not only did I get uniform convergence, but I could give you how many terms I would need to make that less than 1/10,000th. So not only that, I get uniform convergence. That's exciting news. Let's see, I should say here, move that over. For all x. Uniform convergence. If it's C3 smooth, I would get less than m over n squared. And if it's C4 smooth, guess what? I'd get n cubed there. So the smoother it is, of course it'd be different m, so I'm going to call this m twiddle, and this would be m twiddle twiddle. And in fact, ck, I'd get ck minus 1 there. ck and the feeling about that is, let's see, I'll go back to those formulas with those formulas. If f is only C1 smooth, then I can see that that junk in there is continuous. The G is continuous. But if it's C2 smooth, I can show you that that thing is C1 smooth. G of t would be C1 smooth. And then I could integrate by parts. And when I integrate by parts, the sine nt is going to lead to a 1 over n term. You'll see that when you do that first problem in the homework with the sine and the cosine and the sine coefficients. When you integrate by parts, a 1 over n, when you integrate sine nt dt comes out. That's where the 1 over n is going to come from. And same thing with the second function. I just realized the second function is the sine nt, the sine 2t over 2 cancels. So it's even nicer. But I need to, anyway, what I said was valid. I didn't point out that the sine t over 2's there cancel in the h twiddle. Doesn't matter. It's still nice. And if if f was more differentiable, that would be a more differentiable thing, and I could do integration by parts. And the smoother it is, the more integration by parts I can do, and the more times the 1 over n comes out. That's the gut. That's going to work. I can make that work. Question back there?
So the question on the limit of g of t goes to 0.
Yeah.
Be negative 2 times f prime of x.
I think so. What did I write? Oops, thanks for catching that. Yeah, it's f prime at t equals 0. And so you're right. That's important that that be x. So it's continuous there, with giving it that proper value. Which when you're integrating, you can always change the value at one point, and it has no effect on the integral. Okay, so that's the feeling. I guess I got a couple minutes here. I can say a couple words about the history of this subject. Bessel's inequality and that reasoning was interesting in history, because Bessel's inequality shows that those partials converge, those partial sums, Sn converge to f in L2 norm. And that was an exciting moment, because then it doesn't matter what kind of function f is. It can have jumps, etc. It converges in L2. And that's where we discovered the Riemann integral in history. This is the point. That we discovered the Riemann integral is not up to snuff when it comes to that kind of convergence. This is where we discovered that the Riemann integral is defective. Has problems. So functions that converge in L2 in a Riemann